So again, my name is Carter Keating. I am going to be talking right now about kind of basics of interferometry. The core of this lecture is the goal here is to actually give you some idea of how interferometry works in kind of a more intuitive sense. So I'm hoping that by the end of this lecture, you kind of have a physical feeling for what it is that the interferometer is measuring, how it actually operates, and what it is that the data that you have collected actually represents. All right, so let's start with the most basic of questions. What is an interferometer? So an interferometer starts off with an antenna that is a single radio telescope. It turns out that you need not just one antenna, but you need two antennas. And these two antennas together we typically call a baseline. So if ever you hear somebody talking about baselines, they're talking about a pairing of antennas, a particular pair of antennas. All right, so we've got our two telescopes, our two antennas, our one baseline on the ground. Now, let's say we have a monochromatic source that is a source that's only emitting radiation at one frequency of light that happens to be stuck in the same place in the sky, and it's infinitely far away, so we don't have to worry about curvature or relative distance. The relative distance both telescopes basically see the source in the same direction. That's basically how far away it is. So this monochromatic source is raining down sheets of radio photons. My running joke is always, had we been in Hilo, I could make an analogy about the rain, because sheets of rain is a very common phenomenon in Hilo. You just have to kind of imagine all these photons moving together in lockstep, falling through the atmosphere, eventually hitting the radio telescopes. So radio telescopes hit the antennas. The whole job of the antenna is to basically turn that into a voltage, which is carried on cables, carried on a line, and actually brought to a mixer or a correlator. And the whole operation here is basically just that mixer, that correlator is literally just multiplying those two voltage values together. It's the only responsibility it has. It's a very brilliantly simple device. Out of that mixer, out of that correlator, comes what we call the interferometer response. That is what everybody here is measuring. It's measuring the output of this mixer, the output of this correlator, which is mixing together two signals that's coming from two antennas looking up at some celestial source. So diving in a little bit deeper into what this interferometer response actually looks like. So I said we had a monochromatic source. Monochromatic source is the voltage of which we can describe very, very easily, right? It's just at a given antenna, it's either a sine or a cosine. And for here, just for convention's sake, I'll just say it's just a cosine, at least for antenna A. So the voltage as measured at antenna A is just equal to cosine times 2 pi times the frequency times the time. At antenna B, very similar, 2 pi nu times t, but you'll notice this delta term. This delta term is coming up because if you think about the light that's having to come from the source, it's actually having to travel a little extra distance to reach this antenna B. Because of course, the source is coming up from here, the radio waves are moving down and locks up here. They're in phase until here, but they'll hit antenna A first before they'll hit antenna B. So there's this extra lag, this extra delay that the light actually has to travel through before it hits antenna B. That's the source of this delta. So this delta is actually typically referred to as the geometric path delay. Very easy to calculate. All you need to know in this setup are two things. One is that you need to know the vector, the kind of 3D vector that separates the two antennas. That's this capital D here. And then second, you need to know the elevation angle. And then from that, using a little bit of trigonometry, you can actually figure out what the extra travel time or the extra travel distance was for that little bit of light. And as a side note, I'll note that, and I think Dave will talk about this during his imaging lecture, but we talk about unprojected versus projected baseline lengths. Unprojected is the kind of real physical 3D difference. Projected is, you can kind of think of when the photons are all moving in step, the relative distance between these two paths that the light is traveling down. So Anyways, coming back to our voltages here, we have this little delay that's introduced by this little extra travel time that the photon has to travel down. So that is when you have voltage A and voltage B going into a correlator. Like I said, the two things are literally being multiplied together. And for those of you who are too far removed from high school than I am, as I am, to remember all of your trig identities, I promise to double check the math here. And when you multiply those two cosines together, this is literally the quantity you get out. You get 1/2 of a cosine that's at 2 times the frequency that you put in. And then you get 1/2 of a cosine that has no time varying components. The only things that it matters are the frequency, which is not changing, it's a monochromatic source, and then this extra geometric path delay. So this time variable piece, if I average over some period of time, which is pretty common in most forms of astronomy, that piece actually will cancel itself out, such that when I take the average voltage that I measure coming out of this mixer, the things that it primarily depends on are only the frequency of the input light and the lag time. And so you can actually you can describe the voltage as basically just being a function of the lag and the frequency of the light that's coming in. All right, so this is interesting, novel, new, cool. But okay, we've got a measurement, what can we do with it? So let's just kind of play around with it, a little kind of toy experiment here. If I have the telescopes looking straight up, well, straight up, cosine of elevation angle here is 0 because it's looking straight up, or I should say elevation angle here is 0. Elevation angle here is 90. Cosine of 90 is 0. Anything times 0 is 0, so this whole quantity inside becomes 0. Cosine of 0 is 1, and so the voltage becomes a positive quantity. So if you look straight up, you get a positive voltage response. I can dip a little bit further down. I can find it, okay, there's a 0 point off here, and I can find another point that, maybe go a little bit higher, voltage is up here. What you find is that as you trace out as a function of elevation angle, as you can kind of sort of imagine from this equation, you actually see that you'll find this cosine pattern in the sky. This cosine pattern is sometimes what we refer to as a fringe pattern or fringes. Basically, what it's telling you is that if there's a source at a given position in the sky, it will produce either a positive, a negative, or 0 voltage, basically. So a source that's here, here, and here will produce positive voltages, here, here, and here produce negative voltages. And from the interferometer's perspective, it basically takes up the sum of all the sources that it can sense in this fringe pattern. So if you had a source in each one of these peaks and troughs, each one would cancel each other out. So the net voltage would basically end up being 0. Likewise, if you had 5 sources, each one's in the peak, it would be 5 times brighter than just the one source by itself up here. So this is nice, this is neat, this is cool. It turns out actually that you can slightly change this pattern a little bit by introducing just a little bit of delay. And in fact, you can actually jog back and forth the pattern here by making the cable a little bit longer, a little bit shorter. So here I'm injecting a known delay that just happens to be a quarter wavelength. So it's a 90-degree phase shift. The reason why I'm using a 90-degree phase shift here is that it actually contains orthogonal or unique information versus what the cosine pattern has here, right? They are, if you look at these two pieces of information where the cosine sees 0 voltage, on one side, the sine pattern sees positive, and on the other side, the other sees negative. So these two pieces of information are actually unique measurements that you can take simultaneously if you happen to have these two separate mixers, these two separate correlators. So this is actually a fairly common setup in radio astronomy. And in fact, sometimes we refer to the left-hand setup, the one that measures the cosine pattern, as the real correlator, and then the right-hand correlator is the imaginary correlator. I should note that real and imaginary are those are mathematical constructs. That's just kind of convenience when we talk about Fourier transforms. There is no such thing as imaginary photons, or if there is imaginary photons, it's not the things that you're hopefully detecting when you're getting measurements with the telescopes. These are all real photons. It's just the sine or the cosine corresponds to a real or imaginary component in a Fourier transform. And that's why we have this nomenclature. So nowadays, it's much more common that you actually have a correlator that can do both. So it functions as both a real and imaginary correlator simultaneously. All right, so that's great. We've got now two pieces of information. What else can we do with this voltage response? How can we change it or modulate it in some way? Well, one easy way is to just look to the factors that are inside this equation. And the first term that's up front, of course, is this D being the physical separation of the two antennas. So you can actually change the fringe pattern that you're measuring by changing the physical distance between two antennas. And the further out I separate them, the kind of faster in frequency or the more oscillating that fringe pattern gets to be in the sky. And it turns out actually that this is a really, really important thing, because the more sines and cosine patterns that you measure in the sky, if you measure enough of these patterns, it turns out that if you take a Fourier transform, you actually get the exact representation of what the sky looks like. I say exactly because there are some caveats on that, that again, David will actually talk about tomorrow. And so you can actually reconstruct what an image looks like by combining all these different sine and cosine patterns, where the resolution of your image is kind of set by our beloved lambda over d, where in this case, d is the distance between the two telescopes. This sounds a little fantastic. This sounds very weird, right? Why would you stack a bunch of sines and cosines? So I'm actually going to give you a real life example here. Here is the output of my 2-element interferometer looking at some astronomical source. I won't tell you which one, but maybe some of you can guess. And right now I'm going to start stacking on cosine pattern after cosine pattern after cosine pattern. And hopefully, as I start stacking on more and more of these sine and cosine patterns, you start to actually see something, some shape come out of the image. And no longer it looks like this cosine blob or even this kind of weird indistinguishable thing. It actually looks like an astrophysical object. The whole premise of this is called aperture synthesis imaging. It's going to be the primary focus of David's talk tomorrow, so definitely stay tuned for that. But that's how it basically works. You are really just stacking sine and cosine patterns one on top of another in order to be able to reconstruct what the sky looks like, what your astronomical source looks like. So I talked about changing the distance, but of course, I couldn't talk about changing the frequency because we were looking at a monochromatic source. So let's imagine that now instead of just emitting at one frequency of light, now it emits at a bunch of different frequencies. Well, we can actually look at, of course, different wavelengths, right? Most astronomical sources, as Jonathan was actually just talking about, radiate over a range of wavelengths. And so we can change the wavelengths at which our interferometer is looking at. And it turns out that if we look at longer wavelengths, we actually make the fringe pattern slower, or oscillate, we have fewer oscillations across the sky. And likewise, if we look at higher frequencies, we can get tighter, shorter, more compact fringe patterns on the sky. And so you can actually combine different wavelengths of light to recover different spatial scales or different cosine and sine patterns about what the sky looks like. If you look carefully, though, you might notice that there's kind of a weird, it's a little bit subtle, but there is a weird thing that's here, in that you might notice that if I take the sum of all the inputs in the center here, all the wavelengths are coherent. Remember, I said that with an interferometer, you're kind of stacking one thing on top of another. You're not necessarily sensitive to one position of the sky, but all the positions that the telescope is sensitive to. So here, all the wavelengths are actually coherently stacking together. But if you move off, say, not too far away, you notice that there are points where one color of light will actually cancel out the induced voltage of another color of light. So certain spots on the sky actually turn out to be incoherent if you sum across multiple different colors, multiple different frequencies. This is an actual honest to God real effect, and something that we actually have to be cognizant about when we're building radio telescopes. In fact, there's an additional subtlety on this, which is that most radio telescopes don't typically see the entire sky. There are those telescopes that exist, but a telescope like the SMA actually only sees a very small portion of the sky. Field of view of the SMA telescope is about an arc minute. That's roughly the size of Jupiter in the sky. Even telescopes with much bigger field of view, you're typically talking about something like the size of the moon or smaller. So definitely much, much, much smaller than the full sky. And so I'm now looking at a portion of the sky where I've got all these different wavelengths of light basically canceling out, even though there could be a source there. So what do we do? Well, the problem here is that, of course, we have now some set of delays, geometric delays that corresponds to this position in the sky. And so we actually can calculate that mathematically, just like we ran through earlier, and correct for that, and make it so that all the wavelengths of light are actually remain coherent at wherever our field center is. So this is sometimes called fringe rotation, fringe stopping. The point is basically that you adjust the delays so that all of the wavelengths of light, rather than looking like a jumbled mess like this, actually look like this. So they all remain coherent at the center of the field of view. And in fact, as your source moves position, you change it so that you are fringe stopped, so that you are coherent. Oops, wrong way. Whether you're looking straight up or directly on over. So that's basically how that's an additional component that the interferometer has to correct for, is that we actually correct for this geometric delay as part of the correlator setup. So I have, though, introduced kind of a new interesting lever on poking at interesting astrophysical source, right? I told you that you can change the delay and it changes the response a little bit of what it is that you look up in the sky. And so, in fact, you can imagine taking advantage of that by having not just one line going to your correlator, but imagine a bunch of different lines of different lengths, each measuring their own different delay after you've compensated for the geometric and the I, which is the bulk delay component that remains static. So out of that, you get what we can sometimes call a lag spectrum. So here I'm plotting basically the voltage response as a function of the relative lag, the relative travel time through the cables for a different set of delays for basically each cable. This is something. I have something voltage versus time. What good does this do me? Well, it turns out that actually, if you have a bunch of samples in time, by the magic of the Fourier transform, you can actually get a frequency spectrum. That is, you can actually measure the interferometer response versus frequency. This is one way of basically getting frequency information from the interferometer, is to collect multiple lags together, Fourier transform across them, and you can use the interferometer response, or I should say the interferometer response basically sorts out the amount of emission coming from each channel. So if you have a spectral line source, like some of you actually observed over the last couple of weeks, this is basically how it pops out. So this block we usually call a frequency spectrum. The full set of channels, typically refer to that as a spectral window. In SMA terms, we sometimes also call that a chunk or a quadrant, even though we no longer have 4 chunks, we have 6. So sometimes we call it a hextant, a segment, a block. It's got lots of different names. The more commonly used name for the subunits of the individual channels is that frequency channel. I can't think of any other terms for that name, although I'm sure someone will correct me here. So, and it turns out actually that the scales here are actually interrelated. So if you have a full set of, the sampling time in between individual delay channels is tau sub s, and you have n channels, the channel resolution is actually set by the total lag time. That is the difference between the kind of the shortest lag and the longest lag. And likewise, the total bandwidth is actually set by the difference in delay time between the individual lags. So the largest scales on the lag spectrum set the smallest scales in the frequency spectrum, and vice versa. The thing that I basically just described here is typically what's set up that's called an XF correlator. That is, correlate first, then Fourier transform. The SMA and several other interferometers actually invert that, and by virtue of the convolution theorem, you actually can do this. This is mathematically sound. It has a couple of different caveats that we're not going to get into right now, but you can Fourier transform first and then correlate individual frequency channels to basically get roughly the same thing. And that's called an FX channel, which an FX correlator, which is what the SMA uses. All right, so now that I've introduced basically all these things, kind of putting everything together, I now have this really funky, weird looking equation. And it looks kind of scary, but I'm going to step through each one of these things. All right, so R again is the interferometer response. G sub A and G sub B, or we sometimes call them the gain factors. They're basically the instrument's effects, or the instrument's itself kind of imparted on the incoming radio waves. So there's some change in the amplitude, some change in the phase that's induced by the antennas and all the structure that's needed to carry it to the correlator. So they get introduced as part of the, basically as part of the telescope. These can be calibrated out, and in fact, the next lecture is actually going to be talking about calibrating these out. There's what we call the true visibility of the sky. That is the Fourier transform of what the sky looks like given a physical separation between the two antennas. And finally, there's this epsilon, this noise term, which hopefully should get smaller with increased time. So the last piece of this whole setup is that all of these factors, with the exclusion of the noise, all of these factors should remain constant, at least for at least a few seconds, if not minutes or hours. So typically we take not just one set of samples and multiply them together, but of course we take lots and lots of samples, average them all together. And we can get away with that because, of course, most of these values that are inside here, the gains are not changing, the true visibilities are not changing. And the noise, by way of hopefully central limit theorem, should hopefully average down to zero. And so this is this last averaging step basically gets what would be terabytes or petabytes worth of data down to gigabytes, which is processable by your normal modern laptop. All right, so this is basically what the interferometer is measuring. This is what's being output from it. Hopefully you have some physical idea of what it is that the interferometer is seeing up in the sky. The one thing I haven't talked about yet, though, is units or even sensitivity. So I just want to talk about that very briefly right now. Another very messy equation, which I'll jump into for a sec. But first, before I get to that, usually when we talk about some source, some astrophysical source up in the sky, there's a couple of different ways to talk about it. Jonathan talked about specific intensity. The normal unit of measurement for interferometry is typically flux density, or the normal scale, I should say, is flux density. That is the power received per unit area and bandwidth of the telescope. So two different telescopes located on Earth looking at some source should see the same flux density. This is something that's, but for the distance to the source, would be an intrinsic property of the source. Basically, any observer here, any telescope ought to see them measure the same density. Or another way of thinking about it would be specific intensity integrated over a given sky area. So we typically talk about things in terms of flux density and Janskys. If we want to describe what the noise looks like, we have this equation which basically says √2 times Boltzmann constant times system temperature, which I'll dive into a little bit more in just a second. But basically, it's a way of expressing the amount of noise that the telescope is producing on its own in temperature units, in kelvins typically. Divided by the effective area. So bigger telescopes tend to be more sensitive in terms of flux density. And inside this effective area is both the actual physical area of the telescope and also this, what we call aperture efficiency. You can have a very big telescope, but only part of the dish is illuminated and collecting light coherently. And what matters is the product of those two things. And then on the other side of the denominator is square root of bandwidth times integration time. Basically, the longer you integrate or the more bandwidth you integrate over, the more sensitive that you tend to be, or at least the lower the noise fluctuations tend to be. So this is how we typically talk about the sensitivity, or how we describe the noise at the interferometer, and how we can actually calculate the noise at the interferometer. Using just a couple of simple terms that we actually do know about. We do know the bandwidth of the telescope. We do know the integration time. We do measure the system temperature. And I should point out that this quantity that I've written up here, this is only for a single baseline. But of course, multiple baselines, you do typically reduce the noise by root n. There's a caveat that I'm not going to get into just now, but typically it reduces by a square root of n, where n is the total number of baselines in your array. This equation actually harks from something called the radiometer equation, which I think is going to be touched on later. But just to go through it very briefly, it just says that if I have a radio detector, the noise from that radio detector is roughly proportional to the system temperature plus what we call the antenna temperature, all divided by square root bandwidth times time. So antenna temperature is basically, that's basically the brightness temperature as averaged over what the telescope sees. Typically, this is very small, unless you're looking at something very bright like the sun, in which case, it's the temperature of the sun, basically, assuming that the sun fills the field of view of the telescope. The system temperature piece, we typically relate it to what the amount of power that we measure relative to actually sticking in a load at a given temperature. And because it turns out that actually the power should be directly proportional to the total sum temperature the telescope is seeing. So if you stick in, something that's 150 Kelvin versus 300 Kelvin, you should see a factor of 2 increase in the power. So we actually use that. We use something described big, but here it just means fills the primary beam of the telescope. We stick in an absorber, very good absorber at a known temperature, which increases the power some given amount. And actually from that, we're able to calculate what the system temperature is. So the system temperature measurement is actually physically related to actual real physical temperature. And it just happens to be a very convenient and easy way of describing the noise that's coming from the telescope. All right, so hopefully from all that, you have at least some picture in your head of how the interferometer works. Again, we're basically taking what is fluctuations in the electromagnetic field that gets translated into voltage that goes through the telescope, goes into a correlator, and ends up basically telling you something about the flux density of the sky. Interferometers work by effectively synthesizing a much larger aperture from multiple smaller antennas. We're going to be talking about Fourier transforms a lot in many, many places. Turns out to be one of the things that really power interferometers. And I'll just mention very briefly, in comparison to single dish, interferometers are great for doing high resolution and basically getting multi-pixel images with a smaller instrument. Because the detectors that they rely on, they typically have good spectral resolution, and data is usually noise dominated versus systematic dominated for single dish, or can be. But in a synthesized aperture that's 100 meters wide is not as good as a telescope that actually fills, a single dish telescope that fills the aperture. And so single dish telescopes can be more sensitive. The data processing can be less complex. And of course, single dish telescopes are more sensitive to large scale emission versus interferometers, which are typically only sensitive to things smaller than the field of view. So, all right, with that, I will stop there and ask for questions.